Okay, I think we can get started. So thanks a lot, everyone, for joining. So it's a pleasure today to get Oliver Watt-Meyer. So he's currently the climate modeling lead at the Allen Institute for AI. So for those of you who don't know, so that's a nonprofit that was set up by Paul Allen at the time and dedicated very much to AI. And so they have a very strong climate modeling team now as part of that. And initially, so Oliver actually got his BS in mathematics and physics from McGill University. And then he got his PhD in physics from the University of Toronto. And then moved on to actually get a NOAA climate and global change postdoctoral fellow at the University of Washington at the time. And then since he moved to actually get to the Allen Institute, and they've been doing a lot of very interesting work dedicated to using AI initially first for emulation of parameterization, and they moved on to actually basically eat up the entire thing to look at especially atmospheric emulation, and now more and more like full like Earth system coupling between the ocean and the atmosphere. And so they've really been pushing kind of the envelope of what we can do, especially with those emulators, to be as close as possible to realistic and really fast climate simulation. So very much looking forward to your talk, and thanks a lot for joining, Oliver.
All right. Thanks so much, Pierre. Pierre actually also serves on our external advisory council for our team, so it's been great to interact with him and hear all about what Leap has been doing over the last 5 years and more at this point. Okay, so yeah, I'm going to talk about AI for fast and flexible climate modeling. And yeah, this is very much work on behalf of the whole climate modeling team here at AI2, and you can see all the full-time members listed here. Yeah, Pierre did a nice job already introducing a little bit about this, but AI2 is a nonprofit. Our mission is building breakthrough AI to solve the world's biggest problems. A lot of the work is on more traditional AI topics like large language modeling or computer vision, but we have a really strong AI for the environment group within that. It's a bit more applied. And our team's goal is basically to use machine learning and AI to make faster, better, and easier to use climate models. And we don't just work in isolation. We partner very closely with existing climate modeling labs, in particular GFDL at NOAA and Lawrence Livermore National Lab at DOE. So these are longtime developers of climate models, but they're also groups that develop kilometer scale global storm resolving models, which are a fantastic source of training data for machine learning. It's probably a review for most people in the audience, but just to kind of set the stage a little bit, what is how do people plan for climate change currently? A lot of this is based on the CMIP experiments, coupled model to comparison project. So, roughly every 7 to 10 years, all the climate modeling institutions around the world come together and they run a common set of simulations with their latest and greatest climate model. And this has been really useful. These simulations are one of the key ingredients about the confidence of human influence on climate and anticipated changes going into the future. But it's still been hard. These simulations are computationally expensive, so the labs spend a huge amount of time, years doing the simulations and sort of preparing for it all. There are stubborn uncertainties which haven't decreased significantly over subsequent generations of CMIP, and the relatively coarse resolution, 100-kilometer resolution of the models. All these things kind of combine to make it difficult for end users to really take action using these simulations. So basically, our goal is to use AI to improve these sorts of climate models and make this process of actually using climate models for action more straightforward. Quick background again, won't cover it too much, but physically based weather and climate models. Of course, we have modular components for the atmosphere, the ocean, the land, because these are based on the laws of physics. We have some confidence that they will generalize across climates. And the other important thing is that climate is simulated as the statistics of weather, and so we actually are simulating the dynamics at relatively short timescales, and then our climate statistics of interest we get by averaging or taking a max or min or whatever it might be. And in some ways, it's actually kind of interesting. I think it is climate models are in some way the prototype ML foundation model. So we have these large models, but they can be used for many different purposes, both for scientific understanding, climate projection, seasonal forecasting. Often tuned for these different purposes, but the same underlying model, which actually has some nice analogies to modern AI methods. So yeah, where does our team feel like machine learning can come in? And yeah, as Pierre alluded, we've been working on this for a while and kind of working on a trajectory of different strategies where the machine learning tends to do more and more over time. Um, but I think there's a few different avenues. One goal is to actually make models more accurate using machine learning. Another one, which I think is, shouldn't be discounted, is just to make them faster. So the simulations being very slow, or the conventional models being slow, is a real impediment to their use. It's also an impediment to developing the models and making them better, because it takes a really long time to know if your model is better or not if the simulations are very slow. So I think sort of accuracy and speed are both valuable. And strategies that we've taken here, and this is a little more focused on the atmosphere, which has been primarily our area. Um, so one is kind of bias correction, which can either happen online. So as the simulation is running forward, you can have some machine learning model that's kind of coupled to the rest of the physics and the dynamics in the model, and trying to keep it closer to realistic state of the atmosphere. So we've done a number of studies with this kind of approach. Also, of course, post-processing. I mean, this is sort of predates all the modern AI work, longstanding work on sort of bias correction and using statistical methods after your simulation is done. And then, more generally, this hybrid approach of sort of combining physics and AI, not just for online bias correction, but obviously, replacing particular parameterizations or all the physical parameterizations. So this is something that was definitely how our group started, what we were working on originally, and I still think there's a lot of potential in that approach. It is, I would say, very hard, and in particular, like working with existing, Fortran-based models. It's not just a technical challenge, but also kind of more of a fundamental challenge of not being able to optimize the machine learning together with the rest of the physics in the model if it's sort of written in older languages like Fortran. So about 3 years ago, our group started working on full model, what we call full model emulation. So basically, using deep learning and just simulating all the processes in the atmosphere with a single machine learning model. And we were definitely inspired by the fast advances that are being made in the world of weather prediction, where these kind of global AI-based models just trained on reanalysis were showing competitive or better performance than the state-of-the-art numerical models. And so, our question was, well, can we kind of take that as strategy and apply it for climate as well? So this is basically, our approach that we've been following the last few years. And one of our philosophies is definitely to stay inspired by the way that classical, numerical models are, how they operate for climate. And so one of those things is, like I said, seamlessly deriving climate as statistics of weather. And so, although we're kind of interested in sort of long-term trends and changes in time means and things like this, we're still simulating the actual weather, as I'll show later, on 6-hourly or daily time steps. Our team is really focused on climate accuracy. So looking at, if we're getting the right climatology, generalizability to unseen climate. So probing, whether these models can extrapolate in some way. And again, coupling to other Earth system components for climate. Of course, we can't just simulate the atmosphere. We need to have interactions with the ocean and sea ice. And to be able to really address some of these questions, in particular, generalizability in a quantitative way, you sort of need to train on climate model output, not just historical reanalysis. Because if we're just training historical reanalysis, we don't know what the right answer is for future warming. And so by training on climate model output, we can actually kind of rigorously assess the quality of some of these generalization tasks. And it's also, a useful product. If you have expensive numerical model and you train an AI emulator on that, you can get sort of, for certain purposes, an emulator that can do some of the same things, often for 100 or 1,000 times faster throughput and less energy cost. So this is kind of a high level thing. I'm not going to talk about all these advances, but this is just to give you kind of the steps that we've been going through. This has been sort of somewhat systematic progression of kind of adding more components and more features to what these models can do. But yeah, initially, as I said, the focus was just kind of like, okay, we have these people had shown that you could make really accurate 10-day forecasts, but a lot of these global weather models would sort of blow up after a couple of weeks, and no one had really assessed actually whether, even if they were stable, whether they had accurate climatologies. And so that was just kind of where we started, showing that we could get long-term stability and accurate climate. Then sort of the ACE2 models, we're now trying to get realistic historical and future climate change in terms of global mean trends and the pattern of warming. So those models, one of them we could train on Area 5, which is great, and at least works for kind of current climate conditions with some caveats. Or we can train on future global warming simulations, and I'll share some of those results in a little bit. Then we've worked really closely with the M-Squared Lines group at NYU and GFDL and other places, and they had developed Samudra's fantastic ocean emulator. So we worked with them and basically coupled their Samudra architecture with our ACE architecture for the atmosphere, and developed a coupled atmosphere ocean model. We're also, we're interested in making something that's kind of useful for downstream users, and so part of that is going to higher resolution. AI is a fantastic tool, I think very naturally suited for downscaling. So we developed this Hero ACE model, which is emulating XGL. It's actually a 3-kilometer global storm resolving model. So part of that is downscaling back down to the native 3-kilometer resolution. And then most recently, we've been focusing a little bit on the sort of subtle issue of disentangling SST and CO2 forcing for the atmosphere. And I'll come back to that later to explain a bit more what I mean. So this is kind of the high level, and I'll talk about a few of these in more detail now. And if people do have questions, feel free to raise a hand or jump in the chat. Okay, so this will be kind of a brief review. I imagine that at least some people in the audience are familiar with this work, so I'm not going to spend too much time on it. And it's generally, these training strategies are pretty similar to a lot of the global AI weather models, but basically, for the ACE2 model in particular, we have a number of inputs, things like wind, temperature, 8 different vertical layers, surface pressure, and then we use this SFNO architecture. So this is an architecture that's shown is sort of naturally suited for data on the sphere. It operates via spherical harmonic transforms, and had already shown very good sort of long-term stability properties when we started to use it, which is why we picked it up, and this is developed by collaborators at NVIDIA. And then we predict these most of these same sets of fields 6 hours later. We also predict other diagnostics, which are only outputs of the model, things like the surface and top of atmosphere radiative fluxes, precipitation, these important variables which are necessary for things like assessing energy and moisture budgets, or also coupling to the other Earth system components. And that was something that a lot of the other weather models hadn't done yet. And in our initial deterministic models, we basically use a mean squared error loss over 2 6-hour forward steps. And I'll show some results later of our more recent stochastic models as well. So basically the high level view here is we were able to get long stable simulations that also get realistic weather variability throughout those simulations. So this is just showing a video of the outgoing long wave radiation for the first 100 days of a simulation with our very first model, ACE model that we trained. And so one kind of neat thing about this is, although we don't actually specifically prognose or explicitly prognose clouds in ACE, we do see the effects of clouds onto the other predicted variables, like here outgoing long wave radiation, where tropical convection, we have cold cloud tops, we expect less outgoing long wave radiation in regions of tropical convection. So we see that gets reflected in these predictions. But you also see, like on the left here, these predictions are a little bit too smooth. And again, I'll come back to this in the downscaling part and talk about some of our stochastic models, which can improve this issue. So yeah, as I said, we're getting this realistic weather variability, but we can also do these long-term simulations and get the right response to changing external boundary conditions. So this was an example. This is our ACE2 model, which we trained on Area 5 reanalysis. And we provided as inputs to this model both the sea surface temperature, basically as a boundary condition, and also the carbon dioxide concentration, and also the sea ice area. And so when we do all those things, we're able to get a model that recovers the observed historical warming trend. But here we were not testing for extrapolation skill. And so the shading here, basically the white part of the chart is the years that we use for training data. And then the gray shading is for validation and test period. But we can see, we're still only optimizing over 12 hours. So it's actually, still impressive that we can get these 80-year trends. And we do well, even in this sort of interpolated test period. So there's lots more details about this model in that paper here. I'm just going to show one result, and I kind of focusing on this because this is, I would say these two things are things that kind of the coarse resolution GCMs often struggle with. So it's kind of tropical variability and precipitation, things like the Madden-Julian oscillation, and also tropical cyclones in terms of getting the right distribution of tropical cyclones across the planet. And so on the left here is showing the daily mean precipitation rate average between 10 south and 10 north. For the left is from the ERA5 reanalysis. And the second column is our emulator. And this is a 2-year simulation. So we don't expect the timing of these particular events to line up. But you can see that in general, the sort of statistical nature of the tropical precipitation is accurate. And we do get MJO-like events occurring in the ACE2 model. And then also for tropical cyclones, this is, again, just sort of plotting a track over that 10-year holdout period. So although the ACE model somewhat overproduces the number of cyclones according to this kind of tracking algorithm globally, it does get a good distribution across the different basins in terms of where these cyclones are happening. And this is not at all an easy thing to get in a climate model, let alone a coarse resolution climate model. And tropical cyclones have been a neat application. We didn't look into them too much in our paper, but there's been quite a few studies now that have used this model in different ways to probe the sensitivity of tropical cyclones to SSTs and other things like that. Okay, so we talk a little bit about our more recent HERO ACE work. And so here, the goal is, okay, well, we have these amazing, global kilometer scale models. We can look at images of them, and it almost looks like satellite data. Impressive, quote unquote, digital twin fidelity. But these have incredible computational expense. The X-Shield simulation that we train on typically runs on something like 30,000 CPU cores. You get like 0.1 simulated years per day, so you can't really use it for climate. So the question is, can we use AI to leverage these kilometer scale models and make them much faster? And so our contribution here, we call it HERO ACE. So HERO stands for high resolution output, and ACE is the Ai2 Climate Emulator. And so basically the idea was to sort of couple ACE with a local downscaler so you get back to the native resolution. So just give a sense of how this works. So we actually have a 10-year global 3-kilometer X-Shield simulation, which is a fantastic resource. This was a kind of a big push from our collaborators at GFDL. It took about 6 months for this simulation to get done. And there was a lot of obviously technical work and how to sort of process the outputs and save the outputs to not totally break the bank on storage. But a lot of what we do is sort of online coarse graining. So you're only saving kind of a small subset of fields at the full native resolution. And so once we have this 10-year data set, we actually coarsen it, as a post-processing step to 100-kilometer or 1-degree resolution, which is the resolution we use to train our global ACE model. And then we train ACE on this data for basically just making these global predictions at 1-degree resolution. And as I talk about in a second, we also modify ACE to be stochastic, and that helps get the right variability near the grid scale for precipitation and other variables. One caveat here is that 10 years of data is not very much for training one of these global emulators. And in our experience, we can get stable models trained on 10 years of data, but the climate tends to not be very accurate. And it's, the simulations are not the best. And so what we did actually here is we took one of our models that had been pre-trained on the ERA5 data set, which is much longer, and then we fine-tuned that on the shorter 10-year record. That was helpful for be able to get the right actually X-Shield climatology. And then separately, kind of as a totally separate stage, we train a downscaling model, which is now just a regional, kind of patch-based model, which takes in a 16-degree by 16-degree area of the globe, and then downscales it by a factor of 32 back down to the roughly 3-kilometer resolution of X-Shield. And we do this using a diffusion model, somewhat similar to the core diff approach from NVIDIA, although a little bit simplified. We just have one machine learning model, whereas they had sort of two operating in sequence. So once we have these two models trained, we can just plug them together. And actually, one cool thing about this work, which we didn't necessarily expect going into it, is that there was no sort of fine tuning required of the downscaling model on the outputs of the ACE emulator. We could just basically train these things separately and then plug them together, and the results were quite good. And I'll show a couple examples of that later. But basically, at inference time, if we want to make these predictions, now we have this stochastic model with ACE, so we can make an ensemble of possible evolutions of the atmosphere. And then for each of those evolutions, we can also downscale. And since the downscaling is diffusion based, we have multiple possible realizations of that subgrid scale variability. So just showing a couple highlight results. So this is showing the downscaling of a typhoon. And so on the left here, this is just a single 6-hour forecast. So basically, we're initializing our ACE model from basically the X shield data itself, and we just run it forward for 6 hours and get the 6-hour forecast precipitation, and then put that through our downscaler. And on the right is what the actual 6-hour precipitation over that period was from X shield. So you can see over 6 hours, the eye of the hurricane is actually tracking a little bit from southeast to northwest. So that's why it's sort of an oval shaped eye here. And the Hero ACE downscaler is not perfect in terms of getting that exactly right, but we do get realistic maximum precipitation rain rates, which is highly non-trivial. Of course, these are really extreme rain rates, and we do get realistic bands of precipitation away from the center of the cyclone. Amplification of precipitation over land, and a lot of nice features like this. And I will say that downscaling, it's not only, although for this model, we're only doing the downscaling for precipitation, we do have the winds, 10-meter winds as inputs as well. So that gives a lot of useful context for things like tropical cyclones, of course. So that 10-meter northward and eastward winds are also inputs for the downscaling. And then, the other, of course, really natural use case for downscaling is getting the right impact of topography onto things like precipitation. So because obviously the fine res topography is a static field, we can also provide that as an input to the downscaling, which we certainly do. And so what this plot is showing is now a 10-year average of precipitation rain rate from 3 different cases. On the right is the actual X shield simulation. On the left is a free running ACE2S simulation. So ACE2S is what we call the stochastic version of ACE2. So that was the model trained on the coarse index shield data. But again, this is a kind of a global free running simulation, 10 years long. And then if we just take our downscaling model at each 6-hour snapshot, downscale it, and then average those, that's what we get in the middle. So this Hero ACE case. And so we are able to recover the effects of precipitation, of topography on precipitation quite well. There's obviously a lot more details in the paper, but if we actually look at the biases between the middle and the right panels, there are some that are significant, like over the Sierra, where there's a lot of internal variability of precipitation, but ACE seems to have a bit of a low bias in precipitation. But in most regions, the bias is smaller than what we'd expect just from kind of natural variability over 10-year periods. Marcus, do you have a question?
Yeah. Hi. Thanks, Ollie.
Sure.
The Hero Ace, the downscaling was trained on the X shield data. Is that correct?
That is correct, yes.
Okay. And then does X shield have like anything like prognostic aerosols or anything like that, or is it fixed?
Um, I think it's fixed. They're definitely not prognostic. I mean, X-Shield has definitely developed it a little bit more as a weather model, so I don't think it has any kind of sophisticated prognostic aerosols. Yeah,
Okay.
and that
Thanks.
was X-Shield also like it is just an atmosphere only model, so we basically ran it with specified SSTs. So it's using and it's over I think the around 2010 to 2020 period is the training data and when we're evaluating it also. Um, cool. Yeah, thanks for the questions. Yeah, and then coming back to this change that we had to make for the downscaling to work. So basically, um, as I previously showed with that kind of OLR video, which I'm showing again here, the deterministic model tends to smooth out the tropical fine scale structures. So you can see that both for precipitation or for OLR. So basically, this video is showing again a going long radiation for on the right our deterministic model, and on the left our stochastic model. So basically, the stochastic model has noise injected and some layers within the model, and then we use CRPS to optimize the model based on two ensemble members during training. And you see this does really well in terms of recovering the fine scale structures. And so on the bottom is showing this a bit more quantitatively. So it's just the power spectrum for OLR at each of these time steps. And black is what it was for ERA5 at this time. And then in blue is the two versions of the model, so the deterministic and the stochastic. And we're not the only ones to do this. I think this sort of training on CRPS has been a pretty common strategy in the weather prediction world too, to get ensembles of models, and people have shown that this gets better small scale variability. Okay, and then I think our team has always been focused on climate and getting the right kind of answers in a changing climate. And so here I'm going to talk about a few different strategies that we've taken to kind of train ACE on climate change simulations, and basically use it for interpolating between different scenarios or generating larger ensembles. So to address this originally, we wanted to be able to have CO2 be the forcing for this model, and not actually having to be providing the SST boundary conditions. But we didn't want to go to kind of a full-fledged, 3D sophisticated ocean. So we just coupled it to a slab-ocean, which is basically a one-line equation for your ocean, where basically it's just thermodynamic. You have some specified mixed layer depth and specified flux of energy due to dynamics, but those things can't change, or they change over the seasonal cycle, but don't change beyond that. And then the change in temperature of the ocean is just basically coming from the surface energy flux from the atmosphere, which is predicted by ACE as a sum of the various terms in that budget. And so for the first version of this, which we call ACE2 SOM for slab-ocean model, we generated training data from 3 50-year GCM simulations with current present day CO2, doubled CO2, and quadrupled CO2. And then we trained a SOM with CO2 as sort of the key input. And when we did that, we were able to recover the equilibrium climate response to changes in CO2. So this panel here is now showing for a held out case. So basically with tripled CO2, which we didn't train on, the response of temperature from the control climate. On the left is from the actual model that we're training on, and the right from our emulator. And so we did a good job in terms of getting that warming response accurately, and things like the land amplified warming. For these simulations, we did keep sea ice fixed, and so that's part of why you don't see as much Arctic amplification as you might expect otherwise. So for kind of equilibrium climate, and I'm not showing it here, but also for kind of slowly varying climate, like in a simulation where CO2 is going up by 1% per year, we did quite well. But there was a case where we did not get the right answer. And this was basically when we were kind of separately varying SST and CO2, or when these things were not in equilibrium with each other. And so one example of that, and you can see this in a couple of different contexts. So if we take our models that were trained on AMIP, so AMIP simulations, basically where you have sort of the historically evolving SSTs and CO2, but then you trained it with the CO2 going up and the SSTs going up, kind of as they happened in the real world. But then when you do inference of the model, you keep CO2 fixed. And so we know in the real atmosphere, most of the warming in the troposphere is coming from really the rise in CO2. There's not that much of a direct response to CO2 within the atmosphere. And so in the black here, this is what a numerical model does when you keep CO2 fixed but have SSTs going up. You still see a lot of warming in the 2-meter air temperature. Of course, 2-meter air temperature should be very dependent on on sea surface temperature. But in our model, which is the blue line, you can see that when we kept CO2 fixed, there was not enough warming. So it seemed the model was overly sensitive to CO2, which kind of just rises monotonically through the period. So the model can kind of overfit on the CO2. And then for similar reasons on the right here, this is where we basically just abruptly quadruple CO2. So this is like a classic CMIP experiment, part of the standard core set experiments that all the modeling centers have to do. And you can see that our model, if you look at the 2-meter air temperature, much too quickly would just go to the equilibrium of the 4 times CO2 value, and wouldn't really properly respond to the thermal inertia that was being provided by the slab-ocean. And so basically, from a machine learning standpoint, it's basically a data set issue. So if you look at the training data, we were always sort of training on samples where the SST and the CO2 were roughly in equilibrium with each other, and that worked well when we were evaluating the models in that way. And for a lot of purposes, that's okay. But I think people want to use these models and for scientific understanding and do these kinds of experiments, counterfactuals where you keep one thing fixed and not the other. And so I think it's important these models be able to generalize to these other scenarios, which are really common modeling use cases. And so, we designed a new training data set that we could, of course, that's the nice thing about training on numerical model output is you can kind of run whatever simulation you want and use that for training on. And so we basically designed a simulation where the sea surface temperatures were warming over a 5-year period with a uniform 1 Kelvin per year trend. And then we had a time series of CO2 where it would randomly change every 30 days. And 30 days was kind of enough time for the atmosphere to respond to that quick impulse, in particular in the stratosphere, that there's a really big direct response to CO2 changes. And so we did an ensemble of these simulations. And now if you go back to our, the data we're training on, this is kind of showing the phase space of a bunch of samples that we trained on across CO2 and SST. Now we kind of cover this whole phase space with this new data set. And so we trained a new model on basically combination of this AMIP data, some of the equilibrium climate data, and these what we call random CO2 stimulations. And results are that we're now able to do really well on these test cases. And so, these are kind of extreme and not really realistic simulations, but they are really useful for this machine learning model to disentangle these effects. And I think we're quite happy with how well this works. So this newer model, it has actually better skill or comparable skill to the prior 2 different models, which could previously just do AMIP or these sort of slab-ocean experiments. Now we can do both those kinds of experiments with this single model. And it was actually trained on fewer samples than each of those prior models. And then now we can also do these new cases like the abrupt 4 times CO2 on the right, and this sort of AMIP inference with CO2 fixed. And so we're kind of more confident this model's getting the right answer for the right reasons. And happy to talk about this more. I think there are other strategies that we considered, trying to kind of impose more physical priors or kind of use our understanding of how CO2 affects the atmosphere. But I would say this was a case in our experience where sort of the machine learning approach of getting the right data set was really in the end the most successful. Okay, so 2 more kind of things I want to talk about. So first of all, coupled atmosphere-ocean modeling. I'm not going to share too much here, but I think this is really exciting, and I'm looking forward to having more out on this before the end of the year. But again, this was a really close collaboration with the M² Lines group, who developed the Samudra ocean emulator. So if you haven't heard about that, this is basically again an emulator that they had previously trained on OM4, so it's GFDL's ocean model. It's had the same 1 degree horizontal resolution, 19 vertical layers spanning the full ocean depth, and a 5-day time step. is we basically coupled this model to ACE, where basically we have ACE would run forward for 20 steps, and we would average the surface fluxes over those 20 steps to basically get a 5-day mean, and then that would be input to ACE, and excuse me, the input to Samudra. And so again, the point here is that we decided to basically take something similar, not exactly, but I would say fairly similar to what numerical models use and their coupling strategies in terms of the interactions between these two models happen kind of in physical space in terms of the variables that we as climate modelers and scientists kind of know should be the right coupling variables. And so that's the approach we took here, and I think it certainly is very useful for interpretability, and I think it's a good strategy in general. We did also actually have interactive learned sea ice as part of the ocean model, so that wasn't in the original version of Samudra, but when we were coupling to the atmosphere, kind of the sea ice is sort of pretty critical intermediary in the polar regions, and so we basically added sea ice variables as prognostic variables to the Samudra model, so basically included as part of the ocean model. And we trained these on pre-industrial CM4 GCM runs. So again, here we're kind of ignoring varying boundary conditions for now and just sort of try to get accurate and stable long-term climate. And we were able to do this. I think we're pretty happy with how well this worked. You can do long inference with these models. We've run it out for 200 years without any climate drift, and we have pretty small surface temperature and ocean heat uptake biases. And of course, the kind of key thing that you get with one of the key things you get with a coupled model that you can't get with just an atmosphere or just an ocean model is ENSO. So this is the predominant coupled mode of climate variability. So the dashed line here is showing in the just a 40-year period of the CM4 simulation, the time series of the Niño 3.4 anomaly. So this is basically the SST anomaly over a box in the central eastern Pacific. And then in blue is the Samudra model. And so although the overall power is a bit too weak and it tends to be a little bit too regular with the period of around 3 years and not enough power on longer timescales, I still think it's quite impressive that we kind of got this emergent. And so this is something that takes a lot of tuning in numerical models to get right. And this, I'd say more or less just sort of came out of our coupled training strategy, but we're still working on improving the details of this. And then, finally, as I mentioned, Samudra also includes prognostic sea ice, just as part of the ocean model. And we found we were able to do quite well in terms of getting the climatology of the seasonal cycle and the time mean of sea ice in this as well. So this is just showing the seasonal cycles on the left, and then the time mean for CM4 and for Samudra. Just coming back to, why do we want to train models on models? Again, I think a lot of this is the speed and computational cost is a big advantage. So first of all, just, for the training time for the ACE2 models, these things are definitely not free to train, but they're not, there's nothing close to a large language model or anything like that. And so the ACE2 models, which now kind of came out about a year and a half ago, took about 4.5 days on 8 NVIDIA H100s to train. The stochastic models are more expensive because you have to predict 2 ensembles for each training sample. But we are still always exploring strategies to kind of decrease the overall training cost. But really, where these things shine is like once you train the model and we train it and we share these models all openly. People can use them for all kinds of purposes, and they're much cheaper than the traditional models. So this is comparing 2 numerical models with 2 of our AI emulators. So the first of all, the kind of coarse resolution numerical model. I think this is, it's an atmosphere only model, but this is, it's a sort of ballpark what a climate model might cost, probably a little bit cheaper because we have no ocean or other components. But we get about 12 simulated years per walk clock day. 10 simulated years per day is kind of the rule of thumb of how fast your model needs to be really usable for climate. And then X-Shield, of course, is enormously expensive, running on 30,000 CPU cores and only a tenth of a simulated year per wall clock day. And then our emulators are here on the right. So the ACE2 model gets about 1,500 simulated years per day. And Samudra, the coupled model, actually has basically the same cost because the ocean has such a longer time step that it's like almost a negligible cost compared to the atmosphere. And so if you compare that in terms of energy cost, it's about a 750x reduction compared to the atmosphere-only shield model. Comparing the Hero ACE to X Shield is, I think, a little bit trickier to get like the right apples to apples comparison. I think my argument is that AI machine learning is one of the advantages of it is it's much more flexible modeling method than like classical numerical modeling, namely that we can just resolve a few variables of interest just over the region of the planet of interest, at that really high resolution. But we still do it with, I would argue, similar fidelity as to with numerical models, where you basically have to simulate the whole globe to get the right climate everywhere. These AI models can operate at much coarser resolution than the data they're emulating and still be very accurate at that resolution. And that's just a real, I think, powerful thing about these models. And so, again, acknowledging that it's not totally an apples to apples comparison, but if we're just looking at downscaling one 16 degree by 16 degree patch to 3 kilometers, the downscaling model is actually more expensive than ACE because it's based on diffusion, which is kind of expensive at inference time, although we could probably improve this, but we get about 30 simulated years per day. If you compare this to energy cost to X-Shield, which again, this is generating global data, but you get the sort of fantastical, 40,000x, 42,000x energy reduction. Okay. I just have kind of one more little section and then, happy to take some questions and have some discussion after that. So, I think it's been exciting over the last few years. There's been more people coming out with various models. I think a few years ago we weren't even sure if we could train these AI, weather and climate models to be stable, and now there's already, now a handful of groups that have done this. So it's exciting, but we're still kind of in the early stages where everyone was training on slightly different data sets, doing slightly different evaluations, and it was a bit hard to really know how to compare all these models in terms of their sort of quality and abilities. So we got together with a bunch of these groups and other folks as well, and settled on basically a protocol. And actually, all these groups went back and had to retrain their models following this protocol because it did require like a very particular train test split for the data. So it's not just actually evaluating existing models, but people had to kind of go back and train following this protocol. And again, here we're really trying to leverage the track record of CMIP. And so, do that in a couple of ways. First of all, we're doing something that is inspired by one of the classical simulations there, which is so-called AMIP, our Atmosphere Model into Comparison project, where basically it's an atmosphere-only model run with specified SSTs. There's one important caveat that as part of our protocol, CO2 is not an input. Based on our experience, where it's easy for models to kind of use CO2 and get the right answer for the wrong reasons, we thought it was better to just sort of leave that out for now. And also most of the models that were out there didn't actually use CO2 as an input. So that's one important difference. And the other inspiration from CMIP is actually we required all the modeling centers or groups to output their data using kind of the CMIP compliant standards, which makes it much easier for these outputs to then kind of go through all the standard CMIP evaluation tools. And these data sets are available now for anyone to look at, and they follow those standards, which is great. So again, we require all the participants to use the same training and test periods. And in particular, we set this up where basically the test period was an extrapolation case. So, basically training up to 2015, and then can you extrapolate, or if basically now evaluating on 2015 to almost present day. And the participated groups, we participated, Neural GCM from Google, the Climate Model team from NVIDIA, Arches Weather, which is primarily developed at INRIA, the Delisa model from UW, and the University of Maryland group as well. So a good wide variety of modeling approaches, and both academic and industry groups, which is great. Couple of the highlight results. first of all, these models are good at representing the data they were trained on. Not necessarily a huge surprise, but I think still, something that supports our previous findings of these models being able to get really kind of accurate climatologies. So this is showing the root mean squared bias, so basically the RMSE of the time mean for 2-meter air temperature. This is over the training period of the models. Part of that was just because the numerical models that we wanted to compare to, only those AMIP simulations only went up to 2014. So the right bar here is the GFDL AM4 model, which is considered a high quality, one of the other high quality traditional numerical models. And you can see all these AI models do similarly or better than GFDL for this particular case. Of course, these models are like directly trained on ERA5, so you sort of would hope this would be the case. Where we see a lot more differences across the AI models is looking at the long-term trends, both for what's happening in the training period, but then also in the test period. So this plot is showing the global mean average 2-meter air temperature anomaly from the training period. And so in particular in the test period, you can see that there's kind of these two groups where some models, none of them actually replicate the same amount of warming in ERA5. Some of them get fairly close, and then there's others that don't really get much warming at all, including actually the ACE model. So that, again, this is not exactly the ACE to ERA5 because some things have changed here, including not using CO2 as an input. But interestingly, that ACE, when we did not provide SST as an input, was in this configuration insufficiently sensitive to SST, which I'm hoping we'll have some fixes for soon. And then similarly, like we did more extreme perturbations like uniform 4K SST perturbation, which is a very big hammer. And there you see a lot of different behavior across the models, some of which are totally physically implausible, and some of which have some more connection to what we expect based on theory and numerical models, such as amplified warming over land. Okay. With that, I'll kind of just wrap up and then happy to take some questions. First of all, just encourage you all to try it yourself. All the models that I described here are openly available on Hugging Face with Apache 2.0 license. You can actually run these models on CPU. It's pretty painfully slow, but it does work. Running on MacBooks with Apple Silicon actually works pretty well. You get like a 4 or 5x speed up on CPU from my experience. And we also fully openly developed this FME Python package, which we use to train and evaluate all these models. And so you can find this on GitHub. If you have issues, feel free to raise them there. We're certainly happy to get people using these and hear about your experience with it. To sort of summarize, my argument here is that AI models are providing a fast and flexible approach to climate modeling. Our strategy has been to build a efficient, seamless emulator of existing global atmospheric models. So we've shown these are skillful in a range of different configurations. We're starting to do more coupled atmosphere-ocean modeling. We can also integrate these with downscaling models and that way train on global kilometer scale simulations. And again, they're much faster and also easier to run. It's like not a whole thing about installing these models or porting it to a new HPC system. You just sort of pip install and you can go. I still think an open question here and something we're thinking about, but how to best combine the advantages of training on reanalysis, which of course is going to be closer to the real world, and you get these nice features like being able to simulate MJOs and tropical cyclones in the right places, versus the advantages of training on simulation data, where of course we can generate a much wider range of climates. And so it's something we're thinking about, but I think there's still some interesting work to come here. So with that, I'll take any questions.
Thanks a lot, Oliver. So we can open it up for questions. Please raise your hand. And maybe we can start with the junior scientist first. We have one question in the chat, Oliver.
Sorry, let me find the chat. Are you able to read it out? Or?
Yeah, from Paul. Hi, Oliver, great talk. One question. how robust is ACE2, higher ACE when moving from interpolation within the training data to extrapolation beyond the training distribution?
Yeah, I mean, I think it's yeah. So I guess one example was like the AI MIP work I presented at the end. So um, yeah, I think that was a case where extrapolation was not great in terms of getting the expected further warming of the atmosphere in response to increasing SST. I think it depends on yeah. I think there might be some window of extrapolation that is possible. I think it's still a little bit nebulous of what we can expect these um, machine learning models to do. And I think, yeah, there are some questions about whether including some kind of physical priors or limiting, careful design of the machine learning architecture may help in some cases. So there are some differences, I would say, in terms of the architectures from the models that did a bit better in that AI MIP context, where often they had a more like local receptive field, whereas the models that had a more global receptive field seemed to not do well at getting that extrapolation warming. So I think there are some hints there that the design of the model can be important for some of these things. But yeah, I would say in this case, I definitely wouldn't suggest people trust these things for doing something well outside the training distribution for sure.
Thanks. Anyone else? Marcus, yeah, go ahead.
Yeah, nice talk, Oliver. I'm curious, just a detail about the downscaled version of the model. Um, the I assume that the sort of coarse grid values from the high resolution downscaled would match the coarse scale model, right?
Yeah, I mean,
And the fine scale distribution of values is not going to match the fine scale training data model. Is that right? I just want to get that straight.
yeah,
Globally, I
yeah,
guess.
yeah, maybe, yeah. Make sure I understand your question. Yeah, I mean, so no, if you look at, so yeah, I think the one thing to make clear is that the global, like the ACE2 model here on the left, although it's operating at 100-kilometer resolution, like it is trained on the fine scale model because XShield is it's a global model, and so it's trained on XShield, but it's just trained on XShield coarsened to
Oh,
100 kilometers. And so if you just ignore all the scales below 100 kilometers, it actually looks a lot like XShield at the scales of 100 kilometers and above. And that again is sort of what I'm.
okay.
Yeah, one thing
So
that's
so it
interesting
should it
about
should match
yeah
both the
yeah
the high resolution distribution and as well as the sort of coarsened resolution.
yeah, and it does. Yeah, so there's more
Okay.
details in the paper, but yeah, we are able to get like the fine scale precip histogram. Yeah, I mean, there's some extraordinarily extreme events in XShield that we don't quite get, but like by and large, up to the 99.99th percentile does really well. Yeah.
We have another, sorry, my voice is gone. We have another question in the chat from Aman Gupta.
Oh, okay.
Nice
I
talk.
see it now.
Yeah, you
So
can see it.
yeah,
Okay, so maybe
yeah.
you can
Thanks.
go.
Yeah, I found it. Couple. Yeah, great question. And yeah, again, I feel like I glossed over all these papers a little bit. But yeah, in terms of the methodology, we do coupled fine tuning. So that's part of the training procedure. So um, we do pre-train the atmosphere and the ocean separately because it's much cheaper. Basically, once we couple the models together and do training of both models interacting with each other, it becomes quite expensive, mostly because of the difference in time step between the models. If you do like 20 atmosphere steps for every ocean step, and that gets quite expensive. Um, so what we do is basically we pre-train the atmosphere and ocean separately, but then we have found that doing some fine tuning of the interactions between the models is necessary both for getting like time mean climate, and it also does seem to improve variability as well. So yeah, it does be an important part of the procedure.
Yeah, thanks. For some reason, I was not able to raise my hand, so I typed it in the chat.
No worries.
I have a follow-up question. So
Yeah.
does it help that for both the atmosphere and ocean components, you're using GFDL's model? I mean, if you use NCAR's model for the ocean and GFDL for the atmosphere, for instance, Would that be a problem? Like, could you get any distribution shifts or something like that?
Yeah, well, I mean, I think it's definitely useful to have. Yeah, I guess like if all you had was like an atmosphere only simulation and an ocean only simulation, and they were sort of like not never like the training data, like they were never you don't have any training data where you have sort of paired variability between the atmosphere and ocean. I think that would be then you just
Mhm.
wouldn't be able to do any coupled training, and so I think that would
Yeah.
be potentially an issue. Although people have taken like um I think we might get this to work a little bit. So people are looking at like, can we take uh, an AI emulator of an atmosphere model and like couple that to a numerical ocean model? So people have like taken our model that was trained in ERA5 and just coupled it to an ocean model,
Hmm.
and it like kind of worked. I mean, you could get stable simulations, but the ENSO looked a little off. But I think I've seen some work that is making this work a little bit better. So I think there is some possibility that you can kind of take these more um, disparately trained things and put them together, but it'll be
Hmm.
hard, I think, to make it work really well without the coupled fine tuning. Has been our experience so far.
Yeah. Gotcha. Thanks.
Maybe I will take advantage and ask a quick
Mm-hmm.
question. I've been wondering and asking myself the question about the CRPS loss, and you really nicely showed that it improves the kind of, you could say, the spectral divergence, especially at high frequency. And I mean, that's very much what I had in mind, that, you get more and more stochastic at a finer scale, and then it makes sense to go to a CRPS. But then I got curious because we had a paper showing that if you have a latent representation, you could actually roll out on very, very long time scale. So you could still be deterministic and without having a CRPS. And I'm just curious, like, um, why do you think that's actually working? Because I have to say I got confused as to why. Initially, I thought we have to have a stochastic loss, and then I thought like deterministic, like PD solver can maintain, like really high accuracy at the high spectral, like wave numbers, so yeah, just curious about that.
Yeah, I think I guess it comes down to just like the time scales over which you're optimizing. So I think with the deterministic models, like to get the best weather prediction models, they typically have to fine tune out to like 3 days, and I guess that it seems like at that time scale, then we know that the system really is stochastic, and so yeah, we definitely found that like it's determined like we did deterministic loss functions and we're only optimizing over quite short rollouts, then you still maintain a lot of you do better at maintaining the fine scale variability, but optimizing over longer rollouts tended to help for like long-term climate stability and accuracy and that kind of thing. So I think there's a bit of a tension there in our experience.
Yeah, that's a good point.
Yeah.
Thanks. Okay, so I think we are just at the hour. So thanks so much for your time. Very much appreciated your great talk. And yeah, I'll see you soon.
Sounds good. Yeah.
Thanks.
Thanks so much for having me.
Thanks for your time.
Bye-bye.